Okay, good morning, good afternoon, everybody. I'm Kishore Kara. I work for JP Morgan Chase in the Model Risk Group. My team is primarily responsible for identifying risks posed by machine learning models used in different areas of the bank. In this presentation, I will be speaking about identifying and correcting or addressing some of the biases that could be inherent in the machine learning models used in the banking space. So this presentation is specifically in the context of banking. Well, to begin with, we are all aware that machine learning and algorithms are increasingly influencing our decisions and daily lives. We're also growing more and more confident on using the algorithms to make these decisions on our behalf, rather than just using them as decision support systems or recommendation systems. Well, as long as these algorithms are providing suggestions such as picking our movies for us or preferred cuisines for us, they're harmless. But once, primarily because the ultimate decision is still up to us and they're acting only as a decision support system. But when the algorithms are actually making final decisions on an outcome on our behalf, such as in banking space, who deserves a credit card, or who is more likely to commit a crime, be a repeat offender, things like that, then there is a gray area, and we need to be aware of what kind of biases can be introduced into the models. Our inherent human biases, which have found their way into the data, into the model training data, will eventually find a way into the model's outcome and corrupt the machine's decisions. So let's start with the first slide. This particular slide, there are some examples of newspaper headlines of situations where algorithms learned and applied biases from data, causing severe regulatory and legal risks to the organizations involved. To quickly go over some of these examples, some of these stories are pretty famous, you might have heard before. The first one is about Amazon's AI-based applicant screening tool, which was found to be biased in favor of male applicants for software development positions. This was because past 10 years of training data that the model was trained on was dominated by male applicants for these positions, and the machine quickly learned similar behavior. Another example is Microsoft's it's a NLP chatbot known as Tay that was trained using Twitter data. Soon after its deployment, it started tweeting racist rants and was immediately shut down. Another story of an gender-specific unfair treatment is of Apple's credit card. This was in the news about a year ago, which was reportedly providing higher credit limits to male applicants compared with female applicants with similar income and credit histories. And this particular incident paved way for regulatory scrutiny on machine learning models within banking. And a more socially relevant use case is that of law enforcement. AI algorithms are used to predict criminal behavior. Essentially, these algorithms output a single score which indicates the probability of a defendant repeating an offense. Judges use this score in sentencing, and it has been found that these algorithms have discriminated against low-income and minority groups. So it is clear based on these algorithms that bias can creep into machine learning models unintentionally, and it's important to identify the sources of bias before training the model and eliminate the possibility of the biases in the initial stages itself. Bias, which is also known as fairness or lack thereof of a model, and subsequently we need to measure it, and to be able to measure it, we first need to define it. So it's not certainly an easy task to define it, and it could be controversial at times. Let's quickly take a look at a simple mathematical definition of what would be a bias from a model's output point of view. Mathematically speaking, a model whose probability of an outcome is the same, conditional on different subsets of population, can be seen as an unbiased model. Essentially, model outputs are not dependent on a specific subset or specific subpopulation of interest. Philosophically speaking, a bias is just something that you're trying to prevent in the first place. For example, in the example earlier, for a credit card or credit decisioning application, you're trying to prevent the model from disadvantaging any specific subgroup of the population. It's both a philosophical and a moral definition. For some applications in banking, we also need to consider the consequences of the particular model that we're putting in place. And then in banking, we fortunately have some guidance from regulators that provide some basic minimum requirements that needs to be met to ensure that the model is fair. Many popular applications in banking are actually binary classification models. So models that predict a customer probability of default within the next 12 months, or models that predict a particular credit card transaction being fraudulent. So these are all binary. Is it good or a bad transaction, good or a bad credit applicant from a risk point of view? For these models, measuring bias involves calculation of false positive and false negative rates, which can be extracted from the confusion matrix which you see in the bottom right corner of the slide. In many other cases, these are the confusion matrix essentially provides the predicted versus actual outcome in a 2x2 matrix. But in many cases, the measurement may not be straightforward and could require significant business judgment. Now, the next question is, who is responsible for identifying and eliminating these biases? That's what I present in this slide. The short answer is simply everybody that is involved, beginning with the data providers to the model developers, to the users, to the business users, all the way to the legal teams and regulators. Where regulations are involved, it is important that all machine learning model development efforts have initial discussions with legal teams to understand the implications and legal impact of the models. In large banks such as JP Morgan, any machine learning model that was traditionally made by a human requires a legal oversight. So, for example, models used in lending decisions are evaluated for fair lending risk by legal department before the model development begins. Legal team review, the first step is legal team review the input features of the models to ensure that there are no labels that could indicate discrimination, such as demographic information like age, gender, race, etc. within the model training data. Phase of the model, developers need to identify potential sources of bias and try to mitigate it before the training, if possible. Prevention is certainly always better than cure. To mitigate such data biases, developers could gather data from diverse sources and can conduct statistical analysis to measure distributional inconsistencies between different subsets of the population, etc. Second line of defense, at least in large banks, are model governance groups, which I represent. Model governance teams conduct a more thorough analysis on methodologies used for identifying and correcting for biases in the model prior to the model being deployed in production. We also conduct our own independent tests and analyses to identify any biases that could have been missed by model development groups, and subsequent lines of defense involves audit and finally regulators. That brings us to the next slide about relevant regulations. Okay, so though there is no specific regulations that are primarily designed for ML models, a lot of existing regulators have been carried over to the ML space, and banking, as a very heavily regulated industry, has more prevalence of these compared with other industries. Some models, primarily the ones used for credit decisions, for example, are under the purview of regulations such as Equal Opportunity Credit Act and Fair Housing Act. These regulations are designed to avoid any unfair treatments of clients based on personal demographic attributes, for example. And for black box models, which is an ongoing area of research and active area of development within banking, regulators are more recently recommending to develop approaches to increase interpretability and transparency of these models. For example, if the model predicts a probability of default for a consumer application, it is also necessary or recommended to generate reason codes which identify the most important factor or contributor to the default probability, hence providing transparency. And this transparency can also be used in identifying any inherent biases that the model is subject to. And in the Python space, there are packages like such as SHAP and Lime that are being used for model interpretability. And these are being widely accepted by both model development groups, model governance groups, and regulators. With respect to data, the standard SOX compliance, for example, procedures related to data privacy and protection apply. Once the data processing and model training are complete, we can talk about some possible ways in which we can identify biases prior to the model being deployed into production. This slide presents some of these solutions. First, we can conduct something called disparate impact analysis on protected groups to identify if the model is systematically making unfair decisions on certain subset of populations. The way you do it is, for example, by comparing the average outputs between the general population and protected groups, or making more statistical hypothesis testing to identify distributional differences between general population and protected groups. Protected groups need to be identified to begin with. In the case of banking, regulations will provide that guideline, and in the case of other industries, it will probably be based on the business context. If disparity is found, correction is possible by running alternate models, or in some cases, tuning the hyperparameters of the same model differently. If the features that are causing the disparity can be found, then to avoid any regulatory impact, you could try to substitute those features with alternative features which do not inherently show any disparity or bias, but are correlated with the original features while removing the disparity and maintaining the model performance. So if in case improvement cannot be made, the features will have to be dropped to meet regulatory requirements, and which could lead to model degradation. That is unfortunately a trade-off we have to live with. If the input data is severely biased towards one side of the population, then we'll probably have to do some balancing of the data and retrain the model on the subset of the balanced data. Finally, identifying and correcting for biases is not a one-stop process, but an ongoing process. As the regulations evolve and new issues are identified, it is necessary to conduct frequent validation exercises to ensure that the models remain fair and compliant. So with that, we have come to the end of the presentation, and I can answer any questions you have. Let's see in the chat window. So far, I'm unable to see any questions yet. I'll give it a few more seconds. I see a question. Are you generally masking the data before using it in modeling? Right. So it depends on the type of data. There's the PI and the PII data. Highly confidential data is generally not accessible outside of the tight control model group. Model governance, for example, model risk groups do not have access to this data. So you can, if it is highly confidential data and we have no reason to have access to the data, it's probably masked. But in general, there is no necessity to mask data as long as it's remaining within the bank. Anonymizing, yep, I see. So the person is clarifying by masking, I mean it's anonymizing. So if you mean, for example, a categorization of some variables, that is done, but if it's purely from like a privacy protection point of view, would masking solve the bias? Oh, no, I'm not sure if that answers the bias related issue. Let me think about it for a minute. No, So when we say the bias, it is something that is clearly visible in the data. So anonymizing will not necessarily get rid of this bias. When we say from regulatory point of view for the models in banking, within banking, for example, the fair lending related models, we are trying to make sure that features such as gender or race do not play a role in the output of the model. So anonymizing or not anonymizing, I don't think will make any difference, and I don't think it'll have any impact on the bias in these kind of models. Let's see. I hope I answered the question. I'll wait for more.
What's going on? Are you doing a Zoom meeting? Because I don't see anybody. I don't hear anybody. I don't hear anybody and don't see anybody. What's it?
Okay, I guess that brings us to the end of the session. Thank you for your time and apologies for the delay. I'm going to stop the broadcast now. Oops. One more question. Right, so packages in Python for identifying bias. I'm not familiar with any. We have internally built tools that are identifying bias. There could be statistical tools or based on the business context. But what are useful in Python are to meet regulatory requirements are for transparency and interpretability of machine learning models. And I mentioned SHAP and LIME are being widely used for that purpose, and they will eventually. The output of them will eventually be helpful in identifying any biases also. SHAP, short for Shapley, and LIME are the ones I'm familiar with. Okay, thank you everybody. I'm going to stop the broadcast now. Sorry about the delay. Thank you very much.